Here we are. So first, we'll go over some objectives of the presentation. I hope to introduce various testing paradigms and methodologies, discuss the importance of testing, provide examples of these paradigms in action, and discuss how testing can be automated and the importance of doing so compared to manual. And then we have a hands-on exercise where we will be collaboratively working to build a game at the end of the workshop. So hopefully that has caught your attention. And some stuff before we get into everything, I would like, it would be the easiest if everybody had a Java IDE ready. I recommend IntelliJ IDEA 2021 Community. However, Eclipse will work just as well. I cannot personally support VS Code beyond Googling stuff in real time. So if you have VS Code, just try to Google how to set up JUnit with VS Code. I will stop before we start doing the programming exercise to try to get everyone on board with their IDEs should they want to follow along. And I found this really wordy quote that I thought kind of fit this. Testing is an infinite process of comparing the invisible to the ambiguous in order to avoid the unthinkable happening to the anonymous. This comes from some guy named James Bach on Twitter. Seems to be somewhat involved in the testing ecosystem, but beyond that, I don't know anything other than he makes wordy quotes. So there are many different types of testing, and 4 select examples that I think are really prevalent in the software development industry are unit testing, regression testing, integration testing, and acceptance testing. And to an extent, these things are quite related, as a good unit testing library is almost a complete regression testing library. And acceptance testing should really only come after the other sets of testing have been done, because it will waste everyone's time. But I should describe some of these things before I start comparing them to one another. So unit testing involves breaking software down into small, almost atomic units and testing them individually. So in the case of, let's say we're doing unit testing for a Java application, we might want to write a test for each one of the methods in a class. And provided that the test passed, that component worked. That's always the goal. When the tests pass, the component is ready. And this will become exceptionally relevant later when we start talking about test-driven development. Next is regression testing, and the goal of regression testing is to ensure that your software, as it expands and gets bigger, all of the old functionality is maintained and it still works. So let's say you were to add a new module to your project, and somehow it broke absolutely everything you'd done prior to this. It broke something subtle. If it broke everything, it would be obvious. But it broke something subtle behind the scenes. If you had a good regression testing library, you would end up finding this out and being able to fix it without having to encounter this error at runtime. Integration testing, that kind of measures different from the unit test. The integration testing kind of makes sure that the software components work together. So comparing it to the unit test where we're trying to test things atomically and on their own, the integration test tests how well they're able to intermingle with one another. Acceptance testing is usually performed with the product owner, whoever has buying this product, whoever's paying you ultimately, to make sure that the solution you've implemented is up to their standards and it works in a way such that they're satisfied. There are many other types of testing and test sub-ecosystems. There's plenty of it, far too much to talk about in one presentation. So there are a few main things that I believe testing promotes: quality, efficiency, scalability, and agility. So quality. Testing promotes high-quality software by acting as an interface between an idea and an implementation. You have an idea, it might be a great idea, and you need to know if the idea works. Set up a good test, and you can actually put your idea to the test, for lack of a better expression. if the test is well engineered and actually checks everything that's necessary, once the test passes, your idea has become an implemented solution. Testing can lead to the discovery of bugs before they make it into live software. The worst bug is one that happens and it causes a problem for the product owner. Whoever's paying you, if, let's say, there's a company that subcontracts the software engineering firm, they say the software is ready to go, they give the software to the company, and it fails the first day, big grand opening sale, it fails on their face. And you're probably not going to get another contract. You might even get sued for delivering a bad product. So finding these bugs early is very important. In the case of test-driven development, testing provides a great roadmap for design. We'll get a little more into that later, but test-driven development, the testing is kind of the design. We will get into that later. Efficiency. Time is saved when you get a bug, when you find a bug in a test. If something that is not working right comes to light, when you're testing it, instead of, again, in a real-time situation where you might have to go through and debug it, it's great. With time saving comes expense reduction. It costs money to pay developers, so anytime a developer is not doing something or not getting paid, the company saves money. Or they can repurpose the amount they're already paying them to get other tasks done or enhance the product further. And for the sake of documentation and working in a team, having a good testing library can really help get new project members on board. A good unit testing library tests every component of the software. So if all the units of software are being tested with a well-documented library, one can actually consult that testing library to get a pretty well-documented answer as to what everything is supposed to be doing. Scalability. As a project gets larger, we touched on the integration testing and regression testing earlier, a lot of different components and units will start acting together. And as new things get introduced to the system, there's a higher probability for error, provided there's more components working together. There's a chance that there's no new errors. You can introduce as much as you want perfectly programmed software, but I don't think that is too exemplary of a real-world situation. So making sure, let's say, we'll hone in on regression testing, making sure that everything you introduce doesn't break anything that already exists by rerunning the tests that you wrote before, those old unit tests for, oh, we decided the software is ready, now we release something new. After we put something new in, without even any integration testing, we can run those old unit tests. And once those old unit tests confirm that no new problems have been introduced, we can start seeing how these two components interact with one another. As far as integration testing is concerned, you should make sure that new things you introduce to your software work with the old thing. Make sure that they can directly interact with each other as intended, because when you start getting into unintended behavior, you start getting into a bad product. Next, unit testing, it really promotes what Agile is all about. If you have a good unit testing library, I think that any testing library, you can really promote agility as Agile talks about it. And I've decided to include the Agile Manifesto here really quick. Basically, for anyone who hasn't heard of Agile, it is a software development project management methodology. And a bunch of people got together, published this kind of manifesto of values. These are the 12 key values or 11 key values that Agile really kind of promotes, and we can hone in on how some of them are impacted by this unit testing. So, highest priority being to satisfy the customer through early and continuous delivery of valuable software. The whole idea of writing tests ensures that the software is valuable because you can't progress until the test passes. And once the test has passed, provided it's a good test, you know it's ready to go. The value's there because you've tested. Welcome changing requirements. Unit testing, it is great for making refactoring an easier process, making it, you can go into it with a lot more confidence, knowing that you have tests, again, for every aspect of every component of your software. So as requirements change, you're able to change your software to accommodate those new requirements. Delivering working, it really applies to all of these. Unit testing is pretty ad, provided the team has the resources to do it. And we will talk a bit about some of the drawbacks toward the end of the presentation. Next, we're going to hone in more specifically on unit testing. I've already kind of geared things in that direction, but good unit tests should be simple, they should be specific, they should be to the best of your ability independent, and importantly, well documented. So we're going to hone in on those 4 things here. Simplicity. They should be kept simple. It does not mean that they should not be thorough, though. While each test should be simple, the amount of tests should be exactly adequate. As many tests as you need to make sure your software is completely functional. If you can cover all of the execution paths, you probably should. If it's not, again, you don't need to test literally like testing all combinations of positive integers when you're going to add things together is unnecessary. And we'll talk about that a bit in the example going further. Next, specificity. They should be specific to one unit of software. I mean, it's in the definition. It's in the very heart of unit testing. We should not try to test too many components of software at once because that goes against the idea of a unit. And through a process called mocking, we can make some of this easier. I'll go into a bit of what mocking is all about soon, but this workshop will not involve any mocking. Independent. Unit tests should be independent of business logic and external dependencies where possible. Really important to separate them from the business logic. Sometimes an external dependency might have to be part of your unit test, and then you can inject it via whatever unit testing framework you have, dependency injection system. They should be written on one machine and able to be run on other machines. There should be nothing on your computer like grand unit test file.txt that you read everything. And if they become too dependent on these things, their utility goes way down. For everyone to be able to have the unit tests and test their software against it, be it through a version control system or other continuous integration methodologies and practices, it is really good to have them available to everyone. If it's too intermingled with your business logic, then you actually need to run the tests in the same production environment that the business logic is actively occurring on. I would not want a live customer transaction to be the one that I'm testing, if at all avoidable. And well-documentedness. If they're well-documented, they serve as software documentation. I won't go too deep into this. I already outlined it earlier. If you are good with commenting and putting README files or whatever it takes in your company or software development team to document things in a way that other people understand it, you can really paint a whole picture of an application or system through these units. I'm going to talk briefly about mocking and stubbing. There's a lot of conflicting literature as to the exact definitions of each of them, but it revolves around the idea of not having the real object and instead using a fake object when necessary in your team. Let's say you've got 2 classes. You've got the car class and the garage class. You're testing the car class. This is a unit test for the car's park car in garage function. You don't need a real garage. You only need something that implements a garage interface, and a very large quantity of mocking solutions, softwares, and ideologies exist out. I think it is important to talk about when we should mock things. And the best examples I can think of that I could even find were sockets and database. Mocking allows you to reproduce certain states that are not necessarily easy to get into. For example, a network communication error. There are plenty of network communication errors that I'm sure I've never even heard of. And much less being able to create it just by my own device using a real socket, that might be difficult. Databases. If you have to test some database functionality, but you don't want to initialize a whole database every time this test is run, mocking is a great example. From Wikipedia, here are some other examples of when we should mock an object. Non-deterministic results, like the current time or the current temperature. If you need your test to run as if it's 8 p.m., and it's usually using the current time, you don't want to be restricted to running that test at 8 p.m. You can just tell the computer through this mock that it's 8 p.m. There are states that are difficult to create or reproduce. I spoke of that. It's slow with the database. Again, initializing that's a big task. You don't want to do any unnecessary work. You can mock components that don't yet exist. And this one will be easier as you start looking at examples of when to do this, but consider you're making, let's say you're making a storefront application, an online shopping cart, and you want to make sure everything with the user's profile and the actual user object are squared away. You can make a fake shopping and just kind of set value. There are a lot of mocking frameworks. This might seem a little bit overwhelming, like, oh, how would I go about doing all these things? What kind of things are involved? People have already done that work. There's a lot of great open source mocking frameworks out there. I will list a few of them here. We've got Mockito, EasyMock, and JMock. These are all for Java, but similar solutions exist for other programming languages. That will conclude the discussion on mocking for today, but it exists, and there's a lot of frameworks out there that can already help. And just to provide a bit of a retrospective on what we've discussed, software testing is huge. I cannot expect to relay everything about it or even 10% of it in this hour-and-a-half long presentation. However, when it's approached correctly, it can increase productivity and reduce costs. And I don't know where that testing promotes came from, but I don't believe it should be there. So, on to the idea of test-driven development. And on the highest level, it's really simple. Write tests first, program the software in a way that will pass. And we'll go a little bit deeper into that. So, you first, with any good software project, you decide what it is you're actually doing. Whether that comes from communicating with the product owner, your project manager, whatever it may be, you have to decide on what it is you're trying to accomplish. Then you want to write a test that would confirm whether or not what you did worked. Then you run the test and it will fail. I think this is kind of an arbitrary, I don't think it's actually necessary. I think it's redundant to run the failing test. You know it'll fail, but the idea is you don't have any code yet. Then you write the simplest possible solution to make this test pass. You refactor that solution to be in accordance with project standards, however your company, development team, or even yourself prefers the final product in terms of source code to look. Step 5 addresses that. And then you want to add the test to a library of other tests to be rerun in the future, and that accomplishes the goal of establishing a regression testing library. Then you move on to the next unit of software. And this actually ensures that every bit of your software is working by the time you're done with it. There's no, your tests work. You wrote good tests in theory. You can write bad tests or non-deterministic tests or tests that lead you astray, but if you have a good test that actually tests everything you need to test about a component of software, once that test's passed, you're confident that that software is ready to go. There are, returning to those same 4 benefits from earlier, as I just said, when the test passes, it's ready to go. You can reduce a lot of design time and promote easy refactoring down the road by performing this test-driven development because you are engineering the test and then the implementation is already built to the test. You're not trying to figure out a good test for something you built beforehand or trying to design something and then running into an issue where it comes to testing it. It is already, the test is written. When the test passes, it's ready to. Scalability, again, we're just going to carry these tests with us for the product's entire life, and we can use and update the unit tests as the product gets older. A lot of the time, without major reworking of the project, the unit tests for a given component will live for many years without being altered if the project is that long. And returning to the idea of the agile software development methodology, it all around, we'll go back to the Agile Manifesto, it helped. We'll hone in this time simplicity. Maximizing the amount of work not done is essential. And this is all about the bare minimum solution to accomplish everything you accomplish. So code coverage is another word that you might see a lot if you're doing some reading about tests and unit testing. Code coverage simply refers to how much code, what percentage of the code you have in your software library has tests associated with it. If you have no tests whatsoever, you have 0% code coverage. If an application, however, has tests for every unit in the project, you could say that the application has 100 code. Oftentimes, in the real world, the number lies somewhere in the middle. You see, 100% code coverage is not necessarily common, and it's up for debate whether or not that's even effective. However, a number that I encountered in my own readings about this said anything below 80% suggests that the developers might not be properly employing test-driven development, or at least not fundamentally, purely. Now, for the rest of the workshop, we're going to be working in Java, and specifically with the JUnit library. JUnit is a unit testing library. It integrates very well with major Java IDEs. It has a lot of support for so many different unit testing tasks. And there you could have a 20-hour course on JUnit alone, I'm sure. So if you're underwhelmed by the features of this library that are presented today, take a moment, do some reading into it, play around with it beyond the examples, and I think you'll see how powerful it is. So a big part of JUnit are compiler annotations. And we are going to take a look at a lot of these compiler annotations today. And I would just like to briefly kind of talk about each of them. So TESS is a compiler annotation that tells JUnit that you're about to run a test, that this next block of code, this next method, is in fact. A parametrized test is similar in that it tells the compiler that the next method is a test, but a parametrized test, as we'll see in the examples, is parametrized. You can pass in different parameters, and by nature, a parametrized test will rerun as many times as it has parameters to pass to it. Display name, that'll be easier to understand with the pictures, but in addition, by default, JUnit will call each test by the method name. However, you can display a different name instead. And again, I'll point that out when we get to that in the images. Value source, this will be easier once again to understand when we get to the images, but value source will tell JUnit where to find values for a parameterized test. Value source, again, we'll see it in a minute. It works when you have one parameter, one argument that you must apply to a method. At method source, this is a bit more flexible than value source. Method source, you're able to use a method that returns a collection or a stream of arguments object, and that, again, we'll see in the examples, to supply more than one argument or parameter worth of data. Then extend with is used for dependency injection into these JUnit. So I'm going to be speaking, and throughout the code, we're going to see these assertions, and an assertion is kind of just like an assumption that we've made something we know to be true, and we want the software to tell us if it's not. It's a problem if we get the wrong value here. So we're going to talk about 3 today, mostly only 2 of them though. Assert equals, and you pass in assert equals an expected value, or not expected. Oh, I actually miswrote that. Give me one moment. Calculated calculated and actual value. So let's say assert equals 3, 4. That is an exception. An exception will be thrown by the compiler because 3 is not equal to 4. Assert equals Tyler, provided all the casing is the same, will return true. It's fine. Assert throws. Assert throws allows you to kind of test whether or not a software is throwing a given exception or not. So we'll see an example of that, and I think it'll be easier to follow that way. That takes the class that the exception is actually an object of, and then it takes a lambda expression as to what code should be throwing the exception. Here is a really simple example of a unit test and kind of what it might look like in the development environment. So this is the method we're going to be testing. It's called add 3 integers. We take in 3 integers as our parameters. We're going to make sure we don't have an overflow on the addition, and then the sum is equal to the sum of the 3 integers we passed into the function. We're going to return that sum. So here is a very simple test. We use the test annotation to tell JUnit that this is a test. We give it a display name. It's slightly different than the method name. I think the capital letter makes it easier to look at and more pleasant on the eye than the camel case that we see throughout the code. And what we're going to do here, we're just going to set 3 values, value 1, value 2, and value 3. And we're going to call our math helper.add 3 integers function on those 3 numbers and assert that the answer is 6. We can see here that IntelliJ has filled in the name of this parameter, actual, and yeah, this test has passed. It's the math helper test class. Add 3 positive integers that's coming from our display name. We get our check marks, and it's looking. Next, we will talk about parametrized tests, and these are much more flexible and easy to work with. So value source allows us to supply an integer, or not just an integer, supply an object, supply some type of data to a unit test. And again, what happens when you run the unit test or a parameterized unit test is it will execute as many times as it has parameters to pass in. So here we can see the unit test ran for the number 1, the number 2, the number 3, 4, 1,000, 2,000, 5,000, and then the max value for integer. And each test passed. The condition we're testing is we're adding in the parameter x, 0, and 0, and making sure the identity property is maintained in that we still have x plus 0 equals. Are there any questions so far before we dive into more examples and into the interactive portion of the workshop? Okay, moving on. Before we even get that, we're going to go and do some examples of the code. Here we go. If anyone downloaded the file, it's a good time to open it now. So we're going to go into the example code folder. We're first just going to do a brief tour of the math helper class. These are just some different methods that we're going to have unit tests for, or that we can discuss making unit tests for. I've already prepared some of them. Add 3 integers, we saw this earlier. Multiply 3 integers, very similar to add 3 integers. I actually didn't program this correctly. If anyone is actually following, you should change these to asterisk. And here we are. We're going to check for the overflow on each of these. This is just a cool little thing that we can do to make sure we don't have integers that aren't reflective of what we think they are. Because in Java, let's say you have max int, 2.147 billion, whatever the rest of that number is, and then you add, let's say, 100 to it, it will wrap around to negative max int, or min int, whatever you'd want to call it, and then go 100 places towards 0. And that would be really deceptive to whoever is using the software and potentially dangerous if the software was involved in the safety and involved in safety. So we're going to take a look at some of these unit tests. I'll try to introduce what they're doing and what they're showcasing. So we saw the add 3 positive integers test. We're going to see, again, this test annotation. We'll see this a lot. Display name. All of the tests throughout here have a display name, but it's not necessary. And if anyone's using IntelliJ, we're able to run these tests all at once. If we just run math helper test, the whole class, we have all passive tests. Great. Or you can run each test individually by clicking on this little symbol next to the test method name. The next, it's very similar to the first one, and it kind of showcases that we're testing all the different things that this function can do. We're going to try now adding 3 negative integers. We pick the same values, -6. Cool. This showcases the parametrized test. We're going to add positive numbers to 0. And this kind of enforces the identity property. We could even call this identity property test. And our value source, we specify that they're ints, and it is equal to an array. This is the kind of array initialization syntax. Between the 2 brackets, you use a comma-separated list of integers. Then we're going to have a parameter x, and this x, again, is ultimately what will be replaced with each of these. When we run this test, we're going to see that each of these values has appeared in the test. And for the sake of everything, we'll just demonstrate that we can very easily add a 25 to the end of this, rerun our test, and we'll see that we now return 25. Awesome. This test down here, we're going to add 3 positive integers parameterized. And I remembered earlier I spoke of value source only working for 1 argument, this int x. So what do we do in the case that we have numerous arguments? Well, we can write a function that we provide 3 positive numbers. I'll show what this function looks like in just a second, but we use the @method source annotation and provide the name of the method. So down here, we have provide 3 positive numbers. I would be better to name this 3 positive integers, but for the sake of everything, we go on. And we're going to return from this function. We see the function does return a stream of arguments. We're going to return a stream.of. And then this arguments thing, that comes from the JUnit Jupyter arguments library. And it allows us to kind of create a comma-separated list of arguments. And I think it'll make sense when I show the test again what these arguments are doing. So the first time software gets run, we're going to pass in x, y, and z. So down here, x, y, and z. Show us down here, 1, 2, and 3, 10, 20, 30, 30, 40, 50, so on and so forth. You can do even more with this than just ints. You could pass in different argument types. Let's say this is 2.5. This would actually cause an issue in our application because we're not built to support doubles up here. But you can pass in different sets of arguments to your parametrized test. Next, we're going to demonstrate the assert throws, and we're going to test the upper bound out of bounds exception with addition. And this kind of demonstrates what assert throws is all about. We're going to assert a runtime exception will be thrown. And I chose runtime exception, really easy to follow here. Throw a new runtime exception. It's one of the most basic exceptions Java has to offer. And this happens in the event that our long value is greater than or less than integer max value or integer min value, respectively. So we're going to assert that there will be a runtime exception thrown by this block here. This block here, this argument, this expression, is saying that we've got a lambda function with no arguments being supplied to it, no parameters, and we're going to perform this. So what this assert throws says once more is that this code here is going to throw one of these. So we're going to run it, and we'll see the test pass. OOB, out of bounds exception thrown on upper bound addition. Let's say, just to demonstrate what this looks like when it fails, we'll check a null pointer exception instead. So we're going to assert that we throw a null pointer. And we do not. We were expecting runtime exception, but we were expecting null pointer exception, but we got runtime. So this shows that you can make sure you're throwing the correct exception in one of these unit tests. This is just a very similar test, but we're calling it on the multiplication function instead. If we multiply the max value of an integer by 2, we have a number that is far too great to be an integer. It is twice the maximum value for an integer, so we should get an exception there. By default, Java does not do this, though, so pay mind to the idea that we're performing this addition. Where are we? Returning to that test, I wrote a very similar stream to provide 3 negative numbers to this. And once we run that test, I actually didn't write that. So now I wanted, before we get into the main exercise / bulk of the workshop, I wanted to see if anyone who's been following along with this can think of things that weren't tested. And there's plenty of things. I deliberately only wrote a few of these to open up this discussion. So we've tested adding 3 positive integers, adding negative integers, adding 1 integer to 0. Tested the upper bounds. Anything else that we can add to enhance this testing library? Yeah, there's no tests at all for multiplication beyond this out of bounds exception. Right. We don't do any tests for negative numbers beyond adding 3 of them. There's plenty of them. So before we move on, let's pick a test. No tests for multiplication. Let's do a simple test for multiply 3 integers. Cool. Start right up at test, display name, multiply 3 positive integers, void multiply 3 positive integers test. Names, I always think with these tests, especially long names, informative names are much better than short names. You'll save somebody a lot of hassle if it's not yourself by providing good names for. Sometimes you'll run into code that you might be maintaining that is named so poorly you have to ask someone else what it even means. Typos are one thing, but when you've named something ambiguously, it can be very difficult to follow. So to test multiplying 3 integers, do int value 1 equals 5, int value 2 equals 6, int value 3 equals 10. We're going to use our assert equals, and we're hoping that math helper dot multiply 3 integers, value 1, value 2, value 3 is equal to 300. 5 times 6, 30, times 10, 300. So we're going to run our test. And it works. Multiply 3 positive integers, test passed. So now we're going to run this math helper test and just verify that our new class, our new test is now running with all the other ones. Multiply 3 positive integers, boom, it's there on our list. Expanding this allows us to see a little better maybe what's going on here. And see how with these parametrized tests, we're able to expand them and see all the different cases they were run with. So that should be some examples of how these different tests might look as you write them. And this is a very, very, very like tip of the iceberg. Not even a shallow dive into the capabilities of JUnit and these various unit testing ideas. However, I have prepared an example of a test-driven development application that I was hoping everybody would collaborate and kind of write together. Whether or not everyone's actually writing the code, I couldn't care less. But if we could get a discussion going every step of the way and kind of collaborate, I think it would be the best way to really enforce some of these ideas and ingrain them in your mind. So the idea I had was we're going to work together to program Connect3. And the idea of Connect3 is that it is a generalization of Connect4, in that we can have between 2 and 10 players and a board of varying sizes. So we're going to return here. For anyone that is not familiar with Connect4, I will show this for a moment, kind of show what the game looks like. You've got a board like this. One player has each color token. You take turns dropping a token down these slots, and when you have 4 tokens, vertically, horizontally, or diagonally of the same color in a row, the player who owns that color wins the game. You take turns, forth. So the rules for Connect3, as I've imagined it here, the game must work for between 2 and 10 players. You must have between 2 and 40 rows and between 2 and 36 columns. These numbers are kind of arbitrary, but I figured the 2 and 36 would allow us to label them 0 through 9 and then A through Z. Then the empty game board tiles are going to look like this. The populated game board tiles will look like this with the symbol for the player who has dropped the token in. That will be in the board square. So let's say this A represents red. In the bottom right-hand corner of our board visualization, we will have this symbol. That symbol. So players will enter their name at the beginning of the game. Players will then choose their symbol. You cannot choose an empty space. You cannot choose the left bracket, the underscore, or the right bracket because they're used in printing the board. The columns are labeled 0 through 9, then A through Z. Players will take turns. Player 1 moves before player 2, and so on. And players will input the last column they would like to drop their piece into. Or players will input the column they would like to drop their piece into, and it will go into the last available location. So following the example we have on the screen, I'm not sure if my cursor is showing, but if it's not, on the far right-hand side of the board, the piece would go on, it would fall with gravity. I mean, you drop the piece. We're simulating that. It goes to the last available space, which is the first space from the bottom that doesn't have a piece in it, in the column that they've chosen to drop it. And at the end of the game, art will be displayed for the winner or for a stalemate. And I have already prepared in that zip file here for Discord a kind of shell for this project that we can now kind of walk through. We have the Connect3 package within our source folder. In here we have 4 different interfaces, and these are just kind of the methods I imagine we would want to implement to make this game work. This is totally, if there's a better way to do it, if there's any other ideas, if there's a way we'd like to change it, feel free. There's nothing really hard-coded into this yet. It's very flexible. Next, we have the actual implementations of these interfaces, and this is where we're going to be eventually programming after we write our unit test. And I do think that this application will take longer than we have allocated to us for this presentation to actually complete, but I do think we can make some very significant headway into sorting it out. So before I go any further into these test classes or anything about what we're doing here and kind of open the discussion up for what we're going to do first, I would like to know if there's anybody who wants to follow along with this but has been unable to import the project into their IDE. So I will assume that everyone is either not following along in their IDE or has successfully done that. So we should now begin discussing how we're going to approach this task. I say we pick one of these interfaces and we start writing the test for the interface. I'm going to give a brief description of what each one is going to do, or what kind of imagine them doing, and then we can consider what writing the tests for them looks like and maybe a good order to address them. So the first one is the Art Manager interface, iArt Manager. The Art Manager will be responsible for drawing the board. You will pass the Art Manager a board. Draw winning art. That will display the art for the winner. So the idea for that was something simple, just player name, they win, and 5 of the player's symbols with a bunch of asterisks. Then drawing stalemate art. Stalemate, no winner. The board can fill up without a winner. It's a draw. We should play that. And that's all the Art Manager is really there to do. It's not even that necessary. We could pretty easily incorporate the Art Manager into the game handler, but I figured if there was anyone attending who wanted more experience with object-oriented programming and passing around different objects, it might be useful to incorporate some classes here. The board interface, we're going to have an initialize function where we kind of make the array that will hold the board. We're going to pass to that function a row count, column count. Then we're going to have a place piece function. This is actually the function that will change this board array around and put a piece down. And then we're going to have a function that allows us to get the board. That will be useful when we actually need to use the board in our game handler. Now the game handler is where I've kind of planned most of the game logic to take place. So we have set board. This will actually bind the board to the game handler. This actually has to have an argument that is game board, p game board. So if anyone is following along, just give this set board an argument. We will update the class in a moment. Next, set player count. We are going to store the player count in this game board class. So we can set this player count. This will make it easier to manage the turns and how many people we need to loop through each turn. Next, the play game function. This will kind of actually launch all the game logic. Check win, and it returns an integer. The idea behind check win is it will return an integer if that matches the player who won, a -1 for a stalemate, and a 0 perhaps for no win. Check stalemate. We actually don't need to incorporate the stalemate condition in check win. We have check stalemate. True or false is the game over due to a draw. Register players. This will register as many players as necessary. Then get player info from command line. Each player is going to this will actually build the player objects. Register player will be called by register players and ultimately call this. Get move. This will have the player input a move. And then is valid move. We're going to check which column is you're trying to place. The player interface, much simpler. Get the player number, get the player name, and get the player's piece symbol. So that might be a bit of a mouthful or an earful to kind of start digesting and planning out, but may I suggest we start out by writing the test for the game. We're going to check out what game board currently has. We've got an array of characters that is the game board. This actually stores board. We've got an initialize function, place piece function, and a get. So for the sake of the getter, we don't really need to write a unit test for this. Return m. Although, we actually could probably have a test for that to make sure it got. Cool. So we're going to go into the file labeled gameboard test and start planning out what we need. So we should take a function and write a test. Let's just start somewhere. So I'll do the first one. We'll test out the initialization. We're going to test out how well this board can initialize itself, be of. So we're going to open up our game board test class. We're going to supply a compiler annotation at TESS. It's also worth noting that when you want to generate tests for something, you can take full advantage of the IDE. We can right-click here, generate TESS, and then we're given this little pop-up window. Eclipse does it slightly differently, but Eclipse can generate for you a bunch of JUnit if you want. Let's say we wanted to just use these three right here. Boom. It gives us our test annotations. It gives us the stubs. We'll give this one a display name. Call it initialization. And our goal now is to write a test that will check whether or not our board initializes correctly. And since the board can be of varying sizes, the condition I'm thinking to check is the length of each of the board and that it has the default value in it for each entry. So we should establish that a default value on the board, I should have put this in the specification here, a default value in the board will add 0 to the list of symbols we can't have. A character of 0 will be the value in the board. If a tile has a 0 in the actual board array, that is tile is. So what I'm thinking is we need to make a new game board. Game board test board equals new game board. Game board dot test board dot initialize. Let's call 5 5. It's going to be a 5 by 5 game board. Assert equals test board get board length 5. Then we also actually, do you know what? Put this in two different. We'll test that this is 5. And then we'll also test the width in its own test for the sphere. Initialize width test, initialize height. In the spirit of testing things individually and atomically, we're going to write these two separate tests to see that work. Get board. And we're going to check the length. This. So this will check the width. This will check the height the board, and we're now going to run the test and see if it works. Oh, it made a second game board plot. Just take this from over here because I use the generate function. Move it right along into the other class that I'm actually run. Okay. So we're going to run our first test for initialize width. Missing a return statement for get. Return null. For now. We're going to just do return null. Actually, no, that's actually going to be used in this. So we're going to have to do some programming. But now we're going to see that our test, we're going to check, sorry, getting a little off. We have to fix the compiler errors. I changed them earlier. Forward. Okay. Without further ado, we're going to run our test to see if our array is of the correct width. It's not. We've got a null pointer exception because we don't have get board. We haven't programmed anything into the game. So now we've got our failed test. We've determined that when we have the correct length of the board, this test will have passed. And now it's time to program. So we're going to be calling initialize. It takes two integer parameters, a row count, column count. So we're going to go over to game board. So what I'm thinking is since we have a member variable that is game board, we can simply set that game board equals new char p column count, no, p row count, p column. So now we have our new game board, or our game board being initialized with a new character array, a two-dimensional character array, and we're going to return to our tests and see if this is enough to get it to pass. Test failed. Well, in order to do this, we're going to need to program get board as well. And this is a little bit against the spirit of unit testing to program this other component, but since it is just a getter method, accessor, we're just going to return mgame. We're going to go back to our tests, and let's see. Oh, our test passed. And while I haven't been writing stuff to the console, we can very easily do testboard.getBoard.length. We can print out the length. We can add a print statement, run the same test again, and boom, will tell us the board. Now here, we already wrote the other test for the height of the board. We can see here that it works. The board is now initialized with its height and its width. So now we need to test that the board is also empty. We can use our test annotation, our display name annotation, and board initialize empty. So we're going to start again, calling game board, test board equals new game board. Game board dot test board dot initialize. We'll use again 5 by 5. Actually, we'll do it even simpler, 2 by 2. Minimalistic. No need for complication. And we now need to assert. Assert equals get board 0, 0. Board 0, 0. And have a 0. So we're going to make sure the first position is 0, 0. We're going to make sure the second position is actually 0. Third position, 0. And finally, that the last position in the array, 0. So this should fail. We do not actually expect this to work because we haven't programmed it. We're using char, so we have to wrap these zeros in single quotation marks. And we go back to game to iBoard. We're going to run our test first, see that it fails. And we're expecting 0. We got 0. Oh, this works because the default value for an integer array is 0. That's kind of funny that it works. However, we should still go and program the game board to work properly. So, game. Oh, I see what I'm running the. So we still need to go back to game board and program the part where we initialize the array for int I equals 0, I is less than p row count. Plus, we're going to game board I j or not j j j equals 0. So these two loops will take care of setting everything in our game board equal to 0. And now we should be able to run our test, get the values we're hoping for. Oh, you know what it is? I didn't. That's. Boom. Okay. So returning here, our test, we are testing 2 by 2. We make sure that all values are 0. There are definitely better ways than with these 4 assertions here to do this, but we can do it this way, and if even one of them fails, our test will. It would be better to call a parametrized test, though, if we want to get detailed output about what numerous parts of our. So now, can we say confidently that our initialize board function is working? If we go back to the game board, the initialize board will create a new array based on the size that the user wants, and it will set all of its values to the default value of 0. We verified that the length and width are correct and that all values do get set to the default value. I would say personally that this is looking pretty good. I would say initialize works the way we're hoping it does. So next, we're going to look at making a test for place piece. We go back to here, place piece. We'll call it place piece test valid place. Okay. So we're going to make sure that a piece that we place in a location that it can be placed goes to where it's supposed to, or can even be placed. So if we return to what this function looks like, we're going to take in a character and a column to place it in. Okay. So game board, test board equals new game board, test board dot initialize to 2. We're going to try to place a character in the 0th column. Or actually, I think it's the 0th chart. No, it's by the, that's the number. Okay. So we're going to initialize the board, size 2, 2, and we're going to try to place a percent sign at position or in column 0. So we're going to want to assert equals p placement column, or not placement column, board, get board, test board dot get board 0, 0 is equal to percent. And once again, my thoughts behind making this test: we need a game board. We're going to initialize it, or instantiate it. We're going to then initialize the actual board array by calling initialize. We're then going to place a piece on the board and see if it goes to the right place. We'll even expand this to call it empty column. We'll give it a name. Empty column valid piece placement test. We're going to run our new unit test. Oh my goodness, the unit test failed. We're expecting a percent sign, but we get a 0. That's not good. We don't want a 0. We want a percent sign. So now that we've written our unit test here, we can go and write the support for this. We're going to go to game board, place piece, character, p character, into placement column. Basically, what we're going to do is game board. Actually, we're going to have to do for int for int I equals 0. I is less than board and game board. So what I'm thinking here is if this value matches up with 0 equals 0, we're going to set the value mGameBoard p placement column I equal to p character. And we're hoping that when we place we're hoping that we find the first space that has room for this character. when we try to place it, or the last space that has room for it, the first space if you're looking at it from the bottom. And just give me one moment to double check algorithm here. So, getting that length. I think I've actually got something reversed here. Give me a moment to square that away. Well, let's try the test. This is actually the kind of point of doing that. So let's go back to our test. Has what I programmed worked yet? And it did. I actually don't seem to have gotten it backward. That's cool. So now we go to game board. We can now place a piece in an empty column. Let's see. We're going to go back to our game board test, and now we're going to write another test. Void place piece test valid placement occupy. And we're going to program this. Does anybody have a suggestion for what we're going to do for the rest of this test? We're going to test whether or not we can place a piece in a column that already has stuff. So before, what we did, we initialized the board, we placed a piece in the 0th column, and we checked to see whether or not our piece actually got placed.
So, so would you want to initialize a new board? And so, so would you put a piece in a column and then, so we're testing if we can put a piece in a column that already has a piece?
Yeah,
So,
I
okay.
think we had it. Yeah.
Oh, okay. So then you'd put a piece in just any column and then see if you can add another piece or
Yeah,
okay.
exactly. And we're just going to check a different index this time instead. Yep, absolutely. So we're going to assert equals testboard.getBoard 0, 1. This is where I might is equal to that. And let's see if this test. Cool. This test works. We are now able to place a piece in there on the board if there's a board. So something we haven't done yet, though, is trying to place a piece in the board that doesn't belong there. And we need to have some type of protection against that, as we have limited to 36 columns. If the user selects something that is outside of 0 through 9, A through Z, we need to throw some type of exception, or we need to handle that gracefully so the application doesn't. So let's do at test at display name test invalid column selection out, because they will do also invalid column selection column full. Void place p. Attempt to place piece in bad column in non-existent column. Okay, so what should happen when we attempt to place a piece in a column that doesn't exist? There's not necessarily a right or wrong answer here, but we need to pick something. This is the decide what you want to do.
Should we throw an error?
An exception. Cool. So we're going to test board dot initialize, call it 5, 5. We're going to now test board dot place piece. Try to place another percent sign. We're going to place it in column 5, which is bad because the columns are numbered 0 through 4. So we'll try to place something there. And now we're going to assert throws. And actually, no, we have to do that. So we're going to check index out of bounds exception. That's the exception that we're going to throw. That's what Java will throw by nature, so I figure we should try to use that if we can. Test board dot place piece percent sign go, and we need our lambda notation here. So no arguments. Assert throws. We might have the import the method. Compiler can do that for us, but in case you don't have a compiler that does that, you're able to do this and import the static method directly from the Maven repository binaries. And here we are. We're going to test that this code here throws one of these. And let's see if it does. It should, yeah. It threw the test. Java does this by default. When you encounter an array index out of bounds exception, it is already tailored to throw an exception. So because our program is already, because of Java, performing in the way we want it to, this test is taken care of without us having to program anything. Awesome. So now we've tried to place it in a non-existent column. We've confirmed that we get an array out of bounds exception. How about we now test whether or not, or how to, placing it in a full column. What should happen when we attempt to place it in a full column? That's actually a good question as to what should happen when we place it in a full column. Perhaps we don't place it. Perhaps we just maintain the value that was there before. Because the place function is called by the board. It only manages, or place piece is only managing, is used by the board to manage its own content. So the game handler can handle anything else. We'll just not replace it. We'll not change the value. Test dropping piece in full column. Void attempt to place piece full column. Do once again. We can even copy and paste this. Efficiency. We're going to initialize a board that's 5 by 5. Actually, we won't do 5 by 5 because that will be more work to test it. And what we're going to do is we're going to place 2 pieces in 0, 0. So this should fill up the board or fill up that column. And now we're going to try to place a third piece in 0, 0. And what we should assert equals 0, 1, or no, test board, get board, 0, 1, do that, sign, 0, 1 equals @ sign. So the idea here, we first place this index 0, 0 of the board. We then place this index 0, 1 of the board. We now try to place this on top of our 0, 1. We want to make sure that this 0, 1 does not get. Let's see what happens. Ah, okay. So it seems we've got a problem. We are expecting to find a I actually don't know what the symbol's called, the at sign, but we get a percent sign. So this could actually be the result of me having things backwards, like I thought I may have earlier. However, so 0, 0 is the row. No, 0 is the row. That is the. So I think this should be. And this is the benefit to doing this because we are able to now fire up our debugger and let's see what's happening right here in our code. Test board, M game board, 0, got 2% signs and 2 zeros. Yeah. So we're seeing here that it does overwrite this value. And why does it overwrite this value? We're not too sure. Let's go into game board and see if we can figure it out. So we're going to now we're going to see what we did wrong. And at first glance, to me, it looks like this looks kind of good. Because we're only resetting the value if the character in that space is equal to 0. However, there is still a chance that I've done all of this. So 0, 0, unit 2. Turn to the debugger briefly. Oh, lost my break. Go back, see what we've got here. So 0. Okay, so this is placing them in rows. I've actually blundered this, and we're going backward. Okay. So it's good that we discovered this through this unit test, and sometimes the functionality that one unit test might not be enough to reveal that what you've written is broken. However, this has allowed us to find a problem with the software. So we're going to see if we can correct it. Trying to place a piece in column 0. So we should actually, it actually turns out that here I had made a mistake with this unit, making sure that we place 0, 1 be a percent sign. Everything is backwards. We're placing these numbers horizontally. So this should actually be 1, 0. No, this test should be 0, 0, 0, 1. No. We're testing the top piece. That 0, 0 is equal. So for this test, we want to make sure 1, 0. Or 1, 0. back to game board here. And place piece. What if we start this instead at gameboard.length -1? Go to as less than or equal to 0. And now let's see if we go back to test, see if this has produced any difference in the which test dropping piece expected 0. So we have a 0. It did not drop the piece in the correct column. We want to make sure here, though, that 0 is equal. And we got a 0 still. So go back into the debugger, throw up the debugger. Throw it on the oh, debug. Dun, 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 dun. Okay. So it appears now that our function is broken completely. All right. At this point, I realize that I have not actually prepared enough of the solutions off the top of my head to these things to bust them out in a timely manner. The goal was to kind of get everybody talking about how to accomplish these tasks, and I don't think I've prepared a captivating enough example or general presentation to accomplish. But I do believe the idea of how to approach these things and writing the tests first, running the failed test, and then programming until the test works kind of shines through in how we've gone about doing it. So instead of me just struggling through this algorithm for the game board, I think to wrap it up, maybe we will try just maybe writing the tests for. Maybe we would write one more test. That doesn't really do anything. Game handler. Yeah, let's do the test for game handler dot check stale. So right now it's got a default value of return false. We'll go to game handler test at test display name check stalemate. And this test will require us to program a few things here, but we can write the test void check stalemate test. And to game handler, test game handler. We're going to need a game board for the game handler. Game board, test board equals new game board. Game board, test board. Dot initialize, we'll call it 2, 2. board, test board, and assert. We should make a mock or a function to set the whole board for the sake of testing. Public void set whole board char. Our character to set board to. Okay, so now we've written this function to set the whole board equal to one character. This isn't really part of the game, but to make testing easier, we're going to do that. Test game handler. And I'll first do test board, set whole board, and we'll make it equal to that. Assert equals test game handler, check stalemate, and this should. So this was another kind of blunder, but check stalemate is going to check if the board is full, i.e. there are no valid places for a move. And in this condition where we set the whole board equal to something, this player would have actually won. But since wins should be checked before stalemates, as the win condition is potentially prevalent under the logic that the whole board is full, the last thing that was placed on the board could have been the winning move. This is kind of loosely logically okay, but bad. We need to now import our assert equals statement, and we're going to run our test, see if the full board has resulted in a stalemate, and it has failed. We want it to be true because our board is full, there's nowhere left to move. However, it's. So we go back to our game board, and now we make this, not game board, our game handler, and check stalemate just returns false. Of course it's not going to return if. Well, actually, we can just do for int I 0, I is less than game board. Board length plus 4 j 0, j the game board. Get board 0, length j plus And what I'm thinking is if we encounter a single 0, we're fine. If we don't encounter a 0, we should return the game. When I say we're fine, I mean we don't have a stalemate and we can continue playing if we find a 0. If we don't find a 0, the game has ended. If game board ij.getBoard ij is equal to 0, we will return true. Otherwise, we'll return. So now we can see here whether or not our unit test is working. Now we're in the game handler test, check stalemate. And we've got a null pointer exception. So let's see why we have our null pointer exception. Line 39 of check stalemate. Game board length less than that. Oh, we never actually did. Game board equals P board. Now we should get past that exception. Cool. So here's the benefit to doing this. We're expecting that it's true, that we have a stalemate. Oh, actually I just have the logic. Return false. So when we encounter the 0, it's not a stalemate, return false. When we don't encounter the 0 but have checked every square, return true. This also has to be a cool. The check stalemate test has finally passed. And that is how we can use this to troubleshoot our problems and aid in the design process. A couple things that might be worth pointing out. This has resulted in some very kind of minimalistic, simple, easy to follow methods. We're only testing one thing at a time and only adding new functionality to it when we've failed another test. And I think that kind of summarizes the idea of test-driven development is that you should only program things in response to a failed. And right from the ground up, if you write tests and fail them before you develop, everything you program will meet that criteria of having failed a test. And I think the most important thing to remember is that these good tests are they can really enhance productivity, can save a lot of time down the road. And while for something as trivial as a Connect3 simulation and a command line, it probably doesn't seem worth it. I bet you half of the people here, if not more, could have programmed this in the time I've been trying to explain it without any of this unit testing. But consider a project that has 100 people working on it, 10,000 different files, and 5 million lines of code. It can become very beneficial to apply this test-driven development mind. The next part that I should discuss before wrapping things up completely is that these unit tests can be integrated with various build tools. When I say build tools, I'm talking Gradle, Apache, and those are two of the big ones. Maven is a build tool. Everyone loves Maven. And basically, what you can do is before you actually run your software, let's say your build tool has like an execute, you want to deploy your software to whatever server, you can actually just tell Gradle or tell Maven to run all of these tests. You can run your entire unit testing library or the most important ones or 80% of the ones needed for your application's function at this point in time. You can run those every single time you deploy the application manually. You know, in practice, every time I would go to like run this game, this test, this actual software, before I actually ran the code, I would run all these unit tests to make sure the software was going to deploy correctly. And that prevents your data from getting destroyed by malfunctioning software. In an actual example of this, working for the courts, we have a ton of different things we have to do. Every new law that gets introduced in New York State has the potential to impact our software. Whether or not we have to change the logic for sealing things, whether or not it's an update to one of our GUI screens to do with charges, everything with all these data exchanges, we're exchanging data with the FBI, we're exchanging data with NICET, other just state policing agencies. And let's say the DSS wants to change their data exchange system. They want to give us a new XML file. That could actually break one of our unit tests, and we can tell them immediately the first time we ever try to run it under that new system, like, hey, something's broken. And then we can work with them specifically because we know exactly what component failed because the tests we have written are specific to those components. I would recommend that anybody who thought this was even remotely worth understanding, or even people who thought it was completely useless, if you left this feeling like you've got nothing, I encourage you to look it up, look into it a bit, and I apologize for failing to explain, because there's a lot of benefits to doing these unit testing and other testing. Another thing is, it's worth mentioning that there are a lot of even more comprehensive testing softwares out there. Think of like QF Test or Selenium that allow you to do more advanced UI testing and create these very dynamic and complex scripts that are able to use reflection to understand everything about your program as it's running and provide even more useful information than JUnit has provided us with today. You can make complex 2,000 step macros to walk through every step of your project and then have the computer do that automatically every time you need to deploy your software. I think that that's a good time to open the floor up once more for questions. I can't help but feel I've kind of let you guys down on this one, but if there's anything I can explain or shed some light on, perhaps we can go out with a bang here.
You didn't let us down, Tyler. This was a good workshop.
Well, I appreciate that.
Yeah. Looks like somebody's typing.
Not a question, but this was
Nice.
oh, cool. Yeah, I would like to. I'll probably publish some follow-up documentation about what this kind of looks like when it's integrated in a larger enterprise setting. But I think that there's a lot to, even if you're working in an environment where this unit testing paradigm isn't very important and people don't immediately embrace it, I think that just about anywhere you have grounds to create that argument, you could make room for this in these software development projects. And while not every project is going to sport a 100% code coverage, something higher than 0 is almost always going to be beneficial.
So so at your job for the state, do you have like a CI/CD pipeline that has unit testing integrated with it? Oh, okay.
Yeah, absolutely. Every single time I go to deploy either the server or the client, thousands of tests are run. We use Gradle for all of our builds. Well, not all of our builds, actually. We still have some ancient stuff using. That's fun to fight with. But yeah, so basically we have a few hundred Gradle tasks that get executed conditionally, and on our main deployment, like let's say I want to deploy the server software locally so I can test any changes I've made to it before moving it into like a further like staging environment or prod. It will run a ton of tests to make sure before the client even considers showing a user interface whether or not it should even continue compiling. And this allows you at every step of the way to even save the time trying to compile the rest of the files when the unit tests. And these build tools allow, that's kind of the whole theory of the CI/CD pipeline, is to keep things rolling and save time where you can. There's a whole field of study or practice emerging right now called developer productivity engineering. Gradle's kind of leading the SEO charge on that one, I think, and there's entire like research departments set up for how to save a minute here, how to save a minute there, how many hours can you save across the company by taking one more step of this process and automating it, or rearranging your process so that the computer can do things more. Another great thing to consider is that unit tests can be run in parallel. If at this point, like when you're launching up the software, you don't need you don't need all the power yet because the software is not even running. You can devote most of the machine's processing power just to powering through the unit. And if some unit tests can't be deemed to be completely thread safe, you can run them numerous times. You can actually create a queue of unit tests to rerun should you encounter failures earlier on in the process and you want to chug along with parallel processing.
How long does it take for your test to finish at work?
So the machine I run off of is a newer i5 with 32 gigabytes of RAM. I think I have 6 cores of processing. It can pound through a lot of them. And the person who's, I'd say, most responsible for writing the core unit tests is a very, very passionate, very proper, pragmatic developer who would write up presentations on the unit tests he'd wrote, explaining why they're good, how they can be improved down the road, what flags are in play. Because not every unit test you write can be perfect. There are a lot of technical limitations or limitations of your product or your resources at the time the test is written that maybe there's just put a compiler put a comment, put a to-do annotation saying, hey, yeah, this part of it's bad. We're using too much business logic, or we shouldn't be dependent on this. We could inject a mock instead. But I would say a lot of these tests run, 10 tests per second, even faster, when the parallel processing gets going. Because considering, let's just go back briefly to the test. Let's go to the example code. Let's see how long it takes me to run all of these tests. No parallel, nothing fancy. 51 ms, 47 ms, 2 ms. So this test where we ran it 8 different times had a total execution time of 2 milliseconds. So at that rate, I could run 500 tests, so 4,000 test cases through this in 1 second. So it can run them very fast without the parallel configuration. And when you get the build tool working to run them in parallel, this could happen almost instantaneously. For these simple tests, and as you get more complicated tests, let's say working through 20 test cases for something really important takes 5 seconds. Okay, that's 5 seconds. It's a lot less time than oh, where did the error happen? Where is this problem? What component did it fail from? It helps you track it down. And I touched on it during the presentation, the idea of refactoring stuff. Let's say the program requirements change. Let's say we're going to add a whole new feature to this tic-tac-toe game or this Connect3 game where the player, once per game, each player can drop a bomb that clears out the next 3 tiles in a row if they're present. And that shifts stuff around. Well, after you've kind of made those changes, you might find a unit test as and because the tests are so simple and so tailored to the actual solution that you're seeking, you'll know exactly where it failed. Combining this with the debugger like we did earlier, you can get a lot of really specific information about it. I think that's a pretty good place to wrap it up. Again, I'll leave the floor open for another few minutes for questions. I really appreciate everyone taking the time out of their day to suffer through this one. And I swear if I ever come back, it'll be something better, something more involved, and something that is a bit more, entertaining. So once more, I thank you, and we'll stay by for a few more minutes to answer questions.
Thanks, Tyler. Um, yeah, I it's unit testing might not be the most glamorous part of software engineering, but it's definitely still one of the key pillars. So somebody has to teach us about it. So thank you.
Well, I appreciate it. Thank you very much once more, everyone, for coming. I am going to head off for the night. Have a good one.
You too, Tyler. Thanks for presenting. We really appreciate it.
Yeah, farewell.
Good night. All right. So yeah, thanks for coming, everybody. And so on Friday we have our uh, last side project development night, and that's pretty much it for the semester.